Hi, in this video, we want to take a look at supervised learning. All right, supervised learning is a type of machine learning. When I put the query out there to the class, almost everybody said they wanted to see machine learning. That was by far the most common thing that the class wants. You want it, you got it. We're going to start working on machine learning. All right, so think about our regression problem. So we were looking at a whole bunch of regression models previously, and you guys had a homework assignment. Well, in regression, we have some kind of numeric value that we're trying to model. So let's say that I build a model, and what I want to do with that model in the future, if I know the predictor values, I want to know what the target value is going to be before it actually happens. That way I have like a crystal ball into the future. Supervised learning is a crystal ball process. My goal is to make a model that predicts the future. That's flat out what I want. Okay, so let's look at an example of this. If I'm looking at the stock market, if a stock is very valuable today, it's probably going to be very valuable tomorrow. Now it might go up, it might go down, it might fluctuate a little bit, but in the ballpark, it's going to be close to where it was yesterday. So a supervised learning model that I could use is I could take today's value to predict tomorrow's value. Now that doesn't really tell me should I buy or should I sell. That just tells me what will the value be. Right, so that is a good, honestly, that's a good model for predicting the value, but that isn't informative because I don't know if I should go ahead and put money in. Should I sell my stocks? What do we do? Should we just sit on it? I don't know. What we want to do, we want to basically use mathematics to come up with a way to predict outcomes before they actually happen. And for today, we're going to be using that soccer data set that we looked at previously during the logistic regression video. Logistic regression is another example of supervised learning. Anytime I have an outcome that I'm trying to predict before it happens, I'm doing supervised learning. All right, so we are still working through an introduction to data science, a Python approach to concepts, techniques, and applications. And we can get the textbook from UCF's library. And here is the website for the textbook. I modified this code. I'm using a soccer data set than the pickle, rather than the pickle file that's in the example here. But conceptually, everything's the same. I wanted to make sure I had a balanced data set because winning and losing is 50-50. There are issues with trying to predict something. We're trying to model something that is highly skewed one way or another. Like if I have very few successes or very few losses or failures, I should say, then there's some things that we can trip over on modeling. So I want to keep it relatively light at this point. And I wanted a 50-50 data set. Winning and losing is always 50-50 because every time somebody wins, somebody else loses in sports. All right, so let's go ahead and get our first packages in. That's matplotlib and pandas. And let's get some more matplotlib going. Now all of this is our data set. And we're just pulling it in. All of this stuff is just a data prep for us to take a look at what's going on, get prepared. And now, what this part is doing is that this is reshaping the data so that I have it stacked on top. So the original data set, if you recall, had it set up so that we have like wins and losses kind of like next to each other, home team, away team. What we want like this, like that. We want stacked on top of each other, and we want coded as win and lose for each individual team. So we're effectively taking the home team data and the away team data, which starts out like this, and we're putting it like that and reshaping it. All right, so now let's go ahead and get X and Y. So this model is taking the number of goals, or this data is we've got the number of goals here in X. X is the number of goals, and that's all of this stuff. You can see it's a bunch of numbers going down and that the team makes. And then 0 and 1 indicates, did they win or did they lose? 1 if they won, 0 if they lost. All right, so now let's go ahead and plot it so we have an idea of what we're getting after. So here's the previous data format of having home goals and away goals, put together in a scatter plot. And it's not as informative as we would like for this purpose. Let's go ahead and do this. All right, so here we can see we've got like 0 goals and a loss, 1 goal and a loss, 2 goals and a loss, 3 goals and a loss. Up here, we have 0 goals and a win, so that would actually be a draw. And then 1 goal and a win, 2 goals and a win, and so on down the line. And so we can see that, with the darkness of the colors, the more goals you score, the more likely you are to win. That's not surprising. Now, this really isn't that good of a predictive model because knowing the number of goals that you score beforehand really isn't that informative for a soccer team, but this is a good place to start. And I hope that this is conceptually interesting. So the idea here is if somehow we could magically control the situation so that we get 2 goals, what's the probability that we're going to win? If we can control the situation so that we have 3 goals, what's the probability we're going to win at the end of the game? All right, so let's go ahead and get neighbors and data set pulled in. All right, so what we're going to do for this model, we're going to do k nearest neighbors. In our data, we're going to look at our predictor variables. We're going to look at, for each individual point, we're going to look at the closest, let's say 1, 2, 3, 5, something like that. We're going to look at the closest points in our predictor variables. And when I say closest, this is going to be in like a higher dimensional space usually. Now here we've only got 1 variable to keep it nice and easy for the beginning. But remember that you've got like a distance equation from your college algebra. Think of it in terms of I've got some points floating out in space. If I got like some points here, all these points are kind of close to each other. All these points here are close to each other. What we do, we look at the number of wins, the number of losses in each group, and then we use the total number of wins and losses to kind of figure out, hey, if we have a new value that is close to these values, these predictor values total, what would be the win or loss? And so this is a voting system, but it's a voting system for every single point of data that we have. All right, so k nearest neighbors and neighbors equals 3. What we're going to do, so we're going to take every time I'll take the 3 closest points and we look and see, are there more wins or more losses among those 3 points? If there's more wins, then we say that that's going to be a win. If there's more losses among those 3 points, we say that that is going to be a loss in our prediction. All right, so what we do for the future. Let's say we have a new data point, like we know the number of goals. What we're going to do, we're going to find the 3 points that are the closest to that new data point, and we're going to see, do those three data points from our training data, do they have more wins or more losses? And then my prediction is going to be that way. So this is, you can think of this as kind of like voting, like each point of the 3 make a vote of win or loss, and however the vote comes out is how it's taken to be. All right, so now let's use KNN fit. So I'm going to fit the model. Now let's go ahead and make predictions on our data set. All right, so here I've got predictions of 0 or 1, depending on how the 3 closest points worked out in the fitting of the model. Now, what's the accuracy? Is this a good model? Is this a bad model? I don't know. Let's find out. What we want to do, what percentage of the time did it get it right? Did it say win and the result is a win? How many times did it call lose and it was a loss? Well, I go ahead and use score on that. I put my predictor in. I take the predictor values, and then what this is going to do, this is going to go ahead and generate the predictions based off of these X values. Then it's going to compare them to the target variable, to the Y value. And we can see that we've got about 68% accuracy. That accuracy is, now, what accuracy is good enough is a very subjective, very situational question. Honestly, if the current model that a company is using is giving maybe, let's say, 64%, and I come up with a model that's consistently 68%, and that difference in percentage results in big dollars, you know what? That's a darn good model. I can tell you at my work, I need about a 90% accuracy before I can launch it. Why? Because the people I work with, the decision makers, really don't understand how hard it is to make good predictions. And so since they want good predictions, I need to be very sharp. For my personal work on my predictive modeling, I have to be very, very accurate, or I do not launch my model. I do not share it. I do not get it out. If you're working in a data analytics group where they understand prediction more, they understand the difficulties of making good predictions with the data at hand, it doesn't need to be so powerful. Now, in this situation, remember that the baseline is going to be 50%, right? 50% win, 50% loss. So if I was just to flip a coin randomly and call win or loss based off of flipping a coin, no information at all taken from the situation, I would get about 50% accuracy. So 68% really isn't that much of an improvement, but it's better than random guessing. So we'll keep on looking at this. All right, let's go ahead and get NumPy in. Now let's go ahead and get a pie plot. So what I want to do, I want to take a look at the actual values in the data set. So here we got true wins and true losses, and we can see that half the time they win, half the time they lose. Not surprising, right? That's how sports are played. Now so as a real coarse look at our model quality, let's take a look. What percent of wins and losses do we have? Does it match the actual population? All right, so we see that we've got 50% win, 50% loss in our model. So our model is consistent with the population that it's attempting to predict, but we can see that the accuracy is actually only 68%. So what this tells us is that when it calls win and when it calls lose, it's equally accurate. You can have the situation where your model is highly accurate for when it predicts win, or it's highly accurate when it predicts loss, but the other one doesn't apply. So this is something I have to start thinking about. That it's not just the overall accuracy, it's when is it accurate and when is it inaccurate we have to worry about. Why do we care? Well, if I'm in a situation we're talking about, like let's say we're doing a drug study and we have a study and our test is the drug has side effects or the drug does not have side effects. Well, if the drug has side effects and we make the wrong call, then people are going to suffer because we launched a medication that has side effects when we said there wasn't. If we say that there are side effects and there aren't side effects, what's the repercussions? Well, the doctor just chooses a different medication, and therefore we don't have to worry about us being the people that hurt the patients. So when we start looking at this, we always need to consider what is the outcome of our mistakes. And when we start worrying about these kind of things, we start changing the weight of our observations, and I'll hopefully be able to include that in this semester. All right, so let's go ahead and take a look at the predictions. So here are the predicted values, call that y hat. Now what we want to do, we want to calculate the number of times that the model said win, and it was a win. we want to calculate the number of times that the model said lose and it was a loss. We want to predict the number of times that the model said win, but it was a loss. And we want to calculate the number of times that the model said loss, but it was a win. So there's 4 possibilities. 2 possibilities are correct. 2 possibilities are incorrect. And so what we're going to do, I'm going to say it's a true positive when, no, you know what, I got this coded wrong. But no, I'm okay. So here the coding is actually positive is a loss and a win is a negative. If I remember correctly. Let's take a look. All right, so here we're looking at the case where we modeled a win and it was a, this is loss. Oh, there's a mistake in my slides. Oh, I am ashamed. I better fix this. I am so ashamed of myself. Pretend that never happened. Pretend it never happened. Okay. Okay, so what we've got going on. All right, so our labels are 0 and 1. So 0, it comes, you know, in order before 1. So therefore, we want the first row to be 0, the second row to be win, first column to be loss because 0 comes before 1. And then we want the second to be win. All right, okay, so this is what's called a confusion matrix. The model declared lose, and the outcome was lose 335 times. Now the model declared lose, but it was a win 195 times. The model declared win, and it was a loss 45 times. The model declared win, but it was a win 185 times. Okay, so when I look at the confusion matrix, first thing to notice is that you see that we've kind of like a diagonal going down here. This entry and this entry are the diagonal. And that's where we want the numbers. We want those numbers to be big. The off diagonal values here and here, those are the errors. Those are the mistakes. When I look at a confusion matrix, the first thing I want to do, I want to kind of eyeball the size of the diagonal, the size of the off diagonal. The second thing I want to do, I want to compare this value to this value. Okay, so here, this is where we're saying we're predicting lose. Here, the model predicted lose and was correct. Here, it predicted lose and was wrong. All right, so I want this value to be bigger than this one. The next thing I want to look at, I want to compare this value to the other value in its column. So here, both of these values are for the outcome of losing. The 335, that's the number of times that the model said lose and it ended up being lose. This tells me how many times it was a loss and the model predicted win. Okay, when I come down here, the next thing I want to check, I want to compare this value to the value above it and beside it. What I want to see the diagonal values bigger than the one in its row, bigger than the one in its column, both like all 4 ways. So here, I see 335. That's bigger than 45. Okay, as a first glance, that's good. And then I see 195. Okay, so let's think about those numbers. Let's say 335 and 195. just kind of eyeballing it. Let's say that's a 3 to 2. So that tells me about 3 out of 5 times and 2 out of 5 times we get, we have the correct result when it predicted loss. Okay, so that's about 60%, 40%. 60. So, and I'm just eyeballing the numbers, just trying to understand it's not precisely correct. But this tells me that when the model losing, when the model predicted lose, about 60% of the time it was correct. Okay. Well, I'd like it to be bigger, but that's the result we get. Now let's come down here. Let's compare 185 to its comparable value. So 185 and 45, just in my head, that's about the same as 20 to 5. And so that's about 80%. So about 80% of the time the model predicted when it was correct. That's reassuring. All right, so what does that tell me? If I use the model, I make a prediction, and it predicts losing, I know that there's about a 40% chance of being right down the road. But if it predicts win, there's about an 80% chance of it being correct. Which one do I have more faith in? Well, if I'm trying to do some betting, well, if it says lose, I'm like, I'm not gonna put money on this one. That's too close. But if it says win, I'm like, yeah, let's do some sports gambling. Yeah. All right, now let's look at this column. I see that I've got 185 and 195. Okay, so given that the outcome was a win, we can see that less than 50% of the time, the model predicted correctly. Okay, so here we can see that there's some issues with the model, that the model's accuracy has a problem when the result is a win. It does much better when the result is a loss. Okay. And so when we start trying to work and improve our models after we have our initial ones, this is the way that we really need to proceed. We need to look at, where are the mistakes and what can I do to improve the outputs. All right, so now let's go ahead and let's generate this all over again. So here is the confusion matrix. So the confusion matrix are these values just put into this format. And it's just a little bit cleaner. And when I use the confusion matrix, function, I can pass that directly to other features of Python to pull out things like sensitivity, specificity, accuracy, and it'll do the calculations for me. All right, so now let's go ahead and let's just repeat this. In the author's code, he repeated this part, so I went ahead and just repeated it anyway. Okay, so now there's some issues with what we've done. What we did, we took the data that we used to build the model and we checked the accuracy of the model using that same data. It works out that if I do this in real life, I'm going to get optimistic results. Machine learning models, think of them as like heat-seeking missiles. Whatever you give them, they will adapt and target it and get on that like nothing else in the world. It will heat-seek out that data. Okay, why is that a problem? Well, there's always a difference between the population we're interested in and the data that we have. There will always be a difference between the two. So I've got some data. I love this data. This is great data, but I actually don't care about my data. I'm not interested in my data. I'm interested in what's truly going on because I'm interested in what's going to happen in the future. There will always be a difference between the two. There's always kind of a gap. So what will happen is that the model, by its sheer nature of trying to fit to the data as sharply as possible, is going to be prone to overfitting. So what I need to do is I need to give myself an honest estimate of what's going on. what the true accuracy of the model will be before I start doing my sports betting. Because I don't want to put money on the table if I don't have confidence in what's going to happen. So here's our game plan. I've got my data, and this is all the data I've got. This is what I've got to work with. I need to build a model and assess how accurate it's going to be. I've got two things. So what we're going to do, we're going to take the data and we're going to break it up. This portion here, I'm going to build the model on. This portion here, what I'm going to do is I'm going to hold it back. So I'm putting this behind my back. This portion of data, I build the model. Okay, so now I am done with this data. I'm done. I'm throwing it away. I'm never going to look at it again. This data, I'm going to pick it up. I'm going to plug it into my model. I'm going to make predictions on that. I'm going to compare the outcomes. I'm going to compare the predicted value to the Y values over here. If they are close to each other, yippee skippy, I'm happy. If they're very dissimilar, I'm still glad that I know that I didn't get something bad. The problem here is if I use the training data to build the model and to assess its accuracy, what will end up happening is it will look better than it really is. And I will get smacked in the face down the road when when the big boss says, "Hey, Aaron, you made all these predictions and they didn't turn out. What's up? What's wrong?" And I'll be like, "Oh, well, it kind of happens. Not a bad situation to be in. The things change." You start making up all these excuses. You don't want to be in that position. I've been in that position not because of bad modeling scheme, not because of partitioning, because features in the data changed between the 12 months that the data was generated, and there was no way to anticipate that outcome. It's not a good position to be in. Try to avoid it. How do we avoid it? We do it by splitting up our data, build a model with one, assess the model with the other. Okay, so here's our game plan. I'm going to take 70% of my data and 30% of my data, and I'm going to break it up that way. And I'm going to break it up randomly. That way, now why am I grabbing my data randomly? I'm breaking it up into the 70-30 in a random manner. I'm doing it this way because I don't want, if let's say the top of the data has a certain feature in it that I'm not aware of. Like there's some hidden underlying aspect to the first observations collected. I don't want to bias my results. So what we try to do, we try to randomly sample throughout. That way we'll hopefully get good outcomes. So what we're going to do here, I'm going to grab NumPy. What we're going to do, we're going to permute all of our data. We're going to randomly shuffle it. Like permutation means just basically mix it up for this purpose. And now permutations are way more interesting than just that, but for our purpose, we're just shuffling the data. So we're taking the rows and we're going like this. We're mixing it all up. All right, this PRC, this is the percentage of training data that we're going to have. And split points, what we're doing is I'm just going through and I'm picking a bunch of values to be the ones that are included in the data and what's not. So what we're doing is we're randomly grabbing some rows of data, 70% of those rows, and we're putting that into our training data set. The training data is the data we build the model on. The test data is the data we evaluate the model on. So X train, Y train. X train is our predictor variables that are randomly pulled out for training. Y train is our target variable with the corresponding rows. You notice that the index here is the same. If I look at this and I look at this, these two indices are the same values. Because they're the same values, I'm grabbing a row of observation and a row of Y values and I'm putting them together in the training set. Now the test set is going to be everything else. Okay, so let's take a look. So we've got 532 rows of data in our training set, and we have 228 rows of data in our test set. So let's go ahead and let's build our model. So what we're going to do is we've got KNN, that's K nearest neighbors, and we're using the closest 3 observations in there. And I go ahead and I fit it on the training data only. So you'll notice that by the splitting, I'm splitting up the data. Since I split it in this manner, I've got like the data that is labeled test has not been touched by this model at all. So if I say KNN dot fit, yeah, I'll just go KNN. I've got a classifier, and we've got, oh, so it's using Minkowski's distance. This is just one of the many ways to calculate distance. Weights are uniform. That means each observation has equal influence on the model. Now, what we want to do is we want to get our predictions. And as a first run, let's go ahead and check to see how does this perform on the data that was used to make the predictions. All right, so I've got about a 74% accuracy on the training data. So this is the data, this is the accuracy on the data that it was built on. This is an optimistic number. Let's check out our confusion matrix. Okay, so first I want to compare. So this is losing row. Model said predict lose, and then we can see that predict lose and it was a loss 221 times. Predict lose and but win 47 times. Predict win and lose 91 times. Predict win and actually won 173 times. So I compare these two values. I compare these two values. I compare these. So the one that's the most problematic of these is when it predicts a win. And so that's not as nice of a ratio as we would like, but yeah, we'll keep on working on building better models. Okay, so now that is using the data that was used to build the model. This is going to probably be an optimistic number. So let's go ahead and let's check on the test set. Let's see what's going on. All right, so we actually have an improvement. Oh, this is a surprise. Oh, it's actually about 78% accuracy. That's an improvement. And here we can see that this doesn't do too shabby. All right, so what if I do it again? Let's see what happens. Let's do this all over again. I'm going to do another random permutation, and I'm going to break it up into 70-30. And we have a new confusion matrix. Let's take a look. Oh, it does not like me doing that. So remember, once I pick out a new training data, I have to go through and rebuild it. All right, so here we got 50% accuracy. Wow, that's, oh, wait, it just, huh, that is interesting. I did not anticipate that. So this is unfavorable. It's just a 50-50 accuracy either way. That's definitely not good. Let's do that. do this again. Let's split it up. What's our accuracy? All right, so it's back up to 75. And then we have about 75 again. This is more typical of what you normally will see. But I want to do this again. I want to do this enough times until I feel like results are a little bit more consistent. All right, 75% accuracy. And 75% accuracy. Okay, that's good. All right, now, something that you always want to look out for when you're doing modeling like this. First and foremost, if you have like a baseline aspect, so I know that half of the results are win. And so if I don't have something substantially bigger than 50%, then there's no use in using my model. Just understand that. So if I have a model that calls out 45% and random guessing would give me 50%, I know I have a bad model. It needs to be substantially bigger than that baseline random guessing aspect would give me. Another thing to check out is, well, let me actually back up. If I had 30% win, then what I could do, I could just call out lose every single time, and that would give me 70% accuracy, right? So in that situation, if I just called out lose every single time, I would have 70% accuracy just off of that. And correspondingly, if I called out lose randomly 70% of the time, win 30% of the time, I would be right about 70% of the time. If it ended up that win was only, and win doesn't really, okay, if I'm making predictions and like a win-lose, it doesn't really make sense to say 70%, but run with me. Just pretend it's a classification scheme more in general. Let's say that we're talking about the situation where I have one classification occurs 1% of the time, the other classification occurs 99% of the time. If I just say that second value every single time, I will have 99% accuracy, right? I mean, it will actually be a pretty good model. So in that situation, for me to be able to use a model, I have to beat that 99%. Now, there are situations where we have to make a decision, and when so something like fraud on credit applications. Well, so fraud is such a rare event, honestly, overall, that let's say 99% is actually a low number for the percent of non-fraudulent applications. If I say, not fraudulent every single time, I'm going to have a very, a very accurate model overall, but I'm kind of missing the point of modeling. So this is kind of what when things get sticky in this classification. All right. Another thing that we want to take a look at, if you look at your train statistics and you look at your test statistics, if these are close together, you probably have not overfitted your model. Train statistics, now almost always your train statistics will be better than your test statistics. Just assume it's going to be that way. If they're close together, and they don't have to be like super tight, but if there's a big difference, then you probably overfitted, and I would use caution before launching the model. The situation where you see that the test statistics are better than the train statistics, you probably have outliers in your training data. And so you probably need to go back and fix that, before you build the model. What you want to do, you want to go back, fix your data, rebuild your model, reevaluate. All right, so let's keep on rocking this. Okay, so now that I've gone off on a tangent, let's take a look at our output. So here the model, that the test statistics overall that we're going to run with, I've got about 76% accuracy. Okay, and then now is 76 good? Is that bad? It depends on the repercussions of mistakes. That's how you have to look at, is this accurate enough of a model? What is the repercussions of being wrong? What's the benefit of being correct? And we have to balance those two when we make a decision on whether to launch a model or not. All right, 134, 21, and 73. So we can see that in this situation, 100 is approximately 3 times as big. And then here, 2 to 7. So, proportionally about the same. 100 to 21 and 34 to 73. All right, so the 73 is about double. Of course, I would like to see there'd be all the numbers be on the diagonal, but this is what we got to work with. All right, so this whole process of randomly permuting the data, splitting up the data, building the model, evaluating the model, all of this can just be ran automatically, because this is one of the nice things about Python. Python in sklearn supports this. Let's let that do all the work for us, and let's not sweat this. Let's not do this manual labor. I went through all this to do it manually just so that we would have an idea of what's going on for this step right here, right now. So I want sklearn model selection. Specifically, I want train, test, split. So it's going to split the data into train set and test set. And once again, we're going to be having 30% as our test percentage. And we're going to split our data into a test size of 30%. We're going to go ahead and use k-nearest neighbor to fit a model. And then I'm going to have y-hat as our predictions. Now let's go ahead and get the accuracy score. And so we can see that's about a 70% accuracy. All right, well, what if we did it again? All right, now it's 76%. 73, 73, 73, 47. Ooh, that's a big drop. 46, 75, 71. All right, so we can see by randomly splitting up our data, building a model, checking our model, it's kind of like a distribution of the accuracy. And this distribution is, personally, when I'm model building, this repeated split and evaluate is how I tackle model accuracy when I build my models. And what I normally do, I actually do 50% on train test. So that way training and test are of equal size. And I'm just kind of pumping it, giving it, getting an idea of what the range of values will be. All right, so now what we want to do, I want to take a look at other model structures. So far, we have only talked about k-nearest neighbor. And honestly, I've never really worked with k-nearest, or I've never launched k-nearest neighbor models ever. Yeah, I've never launched them. The reason why a lot of times we like to talk about them is because they're less mathematical to describe as, building up. Like, how is it that we come up with a prediction? We take the closest 3 points, we do a vote on if it's win or lose, and then we make that prediction. And that's how we work that out. Well, there's other model structures. K-nearest neighbor is talked about a lot. I feel like it gets more hype than it should. I have looked at it repeatedly, and I've never had it be my best model. In any of my personal projects. Now, I work on spreadsheet problems all the time. I do predictions on spreadsheet problems almost exclusively. So non-spreadsheet problems like dealing with like recordings, like sound recordings or video or image processing, I have not done a lot of, but I've done a lot of spreadsheet problems where the data, the data comes in a data frame format, and it's rather than the more exotic, non-traditional machine learning formats. So other ways that we can approach this. So we've got k-nearest neighbors. We also have decision trees. We have support vector machines, and we need metrics to evaluate our model. Okay, so what we want to do, I want to compare all these different types of modeling. Okay, so what we're like in real life, what I'm going to do, I actually build tons and tons and tons of different models, and then I go through and I look for which of these models is the best of the models. And then that's the one or the ones I use for my actual predictions. All right, so what this for loop does, it goes through and for k-nearest neighbors with one neighbor, k-nearest neighbors with 3 neighbors, support vector machines. So this is SVM and support vector machines. This is a support vector classifier, a decision tree classifier. It goes through and it fits a model on the training data. You see how it says train, 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 all the way down. Then it checks the accuracy. Well, it makes a prediction using the test set. Notice that these are the X's. These are the predictor values. I drop the test set predictor values into here. Then after that, I check the accuracy of the 4 different models on this part of the for loop. And what that does is I've got 4 different models, and I'm going to check to see how accurate are each of them. Okay, so let's look at the accuracy. Okay, so you'll see that 10 different times we split the data, and then after I split the data, fit the model, each of the 4 different ways, and then we check the accuracy on those 4 models. So split the data, build the models, then go through and make predictions, check the accuracy. That's one iteration. That is the results. Here, this row 1 is the accuracy from the first go around. Then, for a second time, split the data again, build the models, make predictions, check the accuracy, and record it. That is row 2. And we keep on doing this over and over and over until we get through the number of times I want down here. I picked 10 just because 10 seems good. All right, so I'm looking at this, and it's kind of hard for me to figure out, hey, what's going on here? It's hard for humans to read numbers like this. So let's make a visualization. What we're going to do, we're going to do a box plot. And I know a lot of people hate box plots, but they really are the right way to compare this. What we want to do, we look at the boxes, compare the boxes. What we want for accuracy, we want as big of an accuracy as possible. That means we want the box to be as high up as possible every single time. So we can see if I look at the boxes, the lowest box is k-nearest neighbor with 1 neighbor, then k-nearest neighbor with 3 neighbors, and then we have support vector machine, and then we have the decision tree. So we can see that support vector machine decision tree performed about the same. So if I wanted to make a prediction, I probably would want to use support vector machine or decision tree among these models. All right, well, that's all I've got for you. I hope you're doing well. Take care and let me know if you have any questions.